Hi, everybody. We are going to start a new unit on solving quadratics and complex numbers. And so today I'm going to introduce you to the idea of complex numbers, and you will get a sense of what they are and how they play into solving quadratics. And we're going to link the two together in just a few classes. So let me just start out by saying that up until now, we have been working in something called the real number system. And these are all the numbers that you have ever worked with in your entire life. From the moment you knew about numbers and you can count on your fingers and toes, up to this point, you have always been working in a system of numbers called the real number system. Today, we are going to move to a new number system, one that's called the complex or the imaginary number system. So I'm going to introduce you to something called the imaginary numbers, all right? And then you're going to learn how to perform operations on imaginary or complex numbers. So the goal of today is to perform operations and to understand imaginary numbers. So the first thing that we need to understand is that an imaginary number is a radical, okay? It's a square root. But more specifically, an imaginary number is the result of square rooting a negative number. Now, in the real number system, we know we can't square root negatives because nothing times itself is going to be negative. That's where the imaginary or complex number system comes in, okay? So by definition, we are going to start using the letter I to indicate that the result of square rooting a negative number is an imaginary number. So we use the number, I know it's strange to say this, but the number I, and the definition of I is the square root of negative 1. And likewise, since I is equal to the square root of negative 1, I squared is equal to negative 1. These are the two things that you need to remember when you're working with complex numbers, okay? Remember those definitions. So how do we simplify and perform operations on imaginary numbers? Well, if we ever see that we have to take the square root of a negative number, the first thing we need to do is pull out that square root of negative 1 and turn it into an I. Okay, so let's look at a few examples of what I mean here, okay? So example number 1, we have the square root of negative p. Now, in the real number system, we can't do that. But in the complex number system, we can. Now notice what I did there. I separated the square root of negative p into two parts. The square root of negative 1 times the square root of p, right? So negative 1 times p would be negative p. Now the first part, the square root of negative 1, this is I. And the square root of p, since p is a variable, you can't really simplify it, it remains the square root of p. So how do we write I times the square root of p? Well, we just put the I in front of the square root and we call it I square roots of p, okay? Now, notice the first thing I did always was I pulled out the square root of negative 1. That's going to get our I out from underneath our radical. So how about example number 2? The square root of negative 25. So we break that down into the square root of 25 times the square root of negative 1. Remember, the square root of negative 1 is I. The square root of 25 is 5. So the square root of negative 25 is 5 times I, or 5I. Now notice the two examples here. When we were left with a radical, I put the I in front of the radical. When we were left with an integer, like 5, I put the I after the integer. Okay, so keep that in mind. One more example, the square root of negative 32. All right, so I broke, my goodness, there's a little typo here. I broke that down into the square root of negative 1 times the square root of 32. The square root of 32, okay, that shouldn't be negative 32, positive 32. So we know the square root of negative 1 is I, okay? But can we simplify the square root of 32? Well, when simplifying radicals, remember, we want to try to find the highest perfect square number that's a factor of the radicand. So 16 is the highest perfect square number that's a factor of 32. So I broke 32 down into the square root of 16 and the square root of 2. Okay, 16 times 2 is 32. So square root of 16 is 4, which means when I pull it all together, I have I times 4 times the square root of 2. That's going to leave me with 4i square roots of 2. Okay, hopefully you've done a little bit of simplifying of radicals before. If you remember that you're looking for the highest perfect square number that's a factor of the radicand, then it helps you out. So imaginary numbers are typically written in the form a plus bi, right? So we have two parts, a, which is a real part, and bi, which is what we call the imaginary part, right? So again, we've got a number, which we call the real part, right? 7 in this case is real. And then we have 3i, this is our imaginary part. So it's got two pieces, real and imaginary. And when you have real and imaginary coming together in one expression, we call this a complex number. All right? And in most cases, when you're performing operations with complex numbers, I is kind of treated like any old variable, okay? Like if it were an x or a y or a z. The only thing we need to remember is that when we're combining like terms, just like when we combine like terms with regular expressions, we can only combine real parts together and imaginary parts together. We can't combine real and imaginary together, okay? So let's take a look. Adding and subtracting complex numbers. I think you're going to find that if you looked at these examples, it would look very, very, very similar to adding expressions or polynomials together and combining like terms, right? So all you're doing is combining the real parts together and the imaginary parts together, and you're leaving it as an expression. You treat it just like any other variable. So let's try this one, last one on our own, okay? So remember, we have minus the negative here. So we're going to have to take care of that, which means we have negative 2 minus 3i, and then minus negative 7 is plus 7, and then minus positive 1i is minus I. So combining our like terms together, negative 2 plus 7 is 5, negative 3i minus I is negative 4i. So when it all is said and done, we get 5 minus 4i. Pretty simple, right? Okay, so how do we multiply complex or imaginary numbers together first? Well, in an example like this, where we have the square root of negative 4 times the square root of negative 25, we have to pull the i's out first. I know that sounds kind of gruesome. We have to pull the i's out first, okay? So we just learned how to simplify something like the square root of negative 4. Remember, this was the square root of negative 1 times the square root of 4. This one became the square root of negative 1 times the square root of 25, right? So we have I times square root of 4 is 2 times, there's the I again, times the square root of 25 is 5. If we combine these together, we get 10i squared. 10i squared. Now, if you remember, let's go back up here for a second. Remember our definition. I squared is equal to negative 1. So 10i squared is equivalent to 10 times negative 1, which is negative 10. So the square root of negative 4 times the square root of negative 25 is equal to negative 10. Interesting, huh? Let's take a look at other places where we'll see that I squared come into play, okay? So anytime we're multiplying two imaginary numbers together with i's, right, we're going to get I squared. So if, we can distribute complex numbers like we did here. We can FOIL two complex numbers, right? Or multiply a binomial complex number by another binomial complex number, right? Notice in both of these cases, you end up with I squared. And I squared then turned into negative 1. And we had to deal with that, okay? Let's try this one together. We're going to distribute negative 24i plus 20i squared. Remember what I squared is? I squared is negative 1. So this becomes negative 20, right? Because 20 times negative 1 is negative 20, minus 24i. You're probably asking yourself, wait, why did he put the negative 20 out in front first and then put the imaginary number second? Well, technically it doesn't matter the order, okay? It doesn't matter what order you put the terms. However, most often you will see, in a complex number, you'll see the real number first and then the imaginary number second. So just be aware of that. But you could have left it negative 24i minus 20. It's the same thing. You want to do a distribution? Let's go ahead. So 8 times 8 is 64. 8 times negative 3i is negative 24i. 3i times 8 is positive 24i. And 3i times negative 3i is negative 9i squared. What happens to the two middle terms? When we go to combine, they disappear, right? So we get 64 minus 9i squared. Well, guess what? I squared is negative 1. So this becomes 64 plus 9. And 64 plus 9 is 73. Isn't that weird? So 8 plus 3i times 8 minus 3i is 73. Weird. But really, really interesting. All right, so we talked about adding and subtracting, right? Adding and subtracting complex numbers, multiplying complex numbers. The last thing we need to do is talk about dividing complex numbers. And so one of the things that we need to understand is that in math, it's generally improper to leave radicals in denominators of fractions, okay? It's not horrible, but it's kind of improper. And since imaginary numbers are really just radicals, it's also improper to leave imaginary numbers in denominators of fractions. So what we have to do is we have to do something called rationalizing the denominator. And when we have imaginary numbers, the way we rationalize a denominator is we use something called the complex conjugate. Okay. Interesting. So a complex conjugate is what we're talking about. And it sounds more complicated than what it really is, okay? So if we're talking about, let's just say, we have the complex number a plus bi, then the complex conjugate of that would be a minus bi, okay? So all you have to do is switch the sign of one of the terms there. Generally speaking, you switch the sign of the imaginary part, and by doing so, when you multiply a complex number by its conjugate, all the imaginary numbers should disappear. And it's actually what happened up here, right? When we multiplied 8 plus 3i times 8 minus 3i, we ended up with 73. And 73 didn't have any imaginary numbers whatsoever. So let's see how that actually works, okay? Let's take a look at this example number 1. We have 7 plus 3i divided by 5i. So here's what we're going to do. We are going to multiply the numerator and denominator by the same thing, right? Because that's equivalent to 1. And when we multiply something by 1, we don't change the value, we're just changing its form. So what is the conjugate of 5i? It's negative 5i. So we're going to multiply the numerator and the denominator by negative 5i. Negative 5i. See how I did that? This is equivalent to 1, right? So we're just multiplying this by 1, not changing its value. And we have to do a little bit of multiplication. And when we multiply fractions, remember we multiply across the top and across the bottom. So it looks like we're going to have to do a little bit of distribution on the top. So let's take a look at what we get. We get negative 5i times 7 is negative 35i. And then we have 3i times negative 5i, that would be negative 15i squared. Ooh, there's that I squared again. But let's hold off on simplifying that just for a minute. And what do we get when we multiply 5i times negative 5i? we get negative 25I squared. I want to go ahead and simplify a little bit. Take care of those I squareds, right? So remember, I squared is negative 1. So this becomes negative 1. This is going to become negative 1. That makes my numerator, and I'm going to switch the order again, 15 minus 35I. And in the denominator, I've got negative 25 times negative 1, which is positive 25. If you look closely at this fraction, you'll notice that all of the terms are divisible by 5. So we can actually simplify this just a little bit, right? Like, for example, if we factored out a 5 from the numerator and we canceled, right, or we canceled common factors in the numerator and denominator, it'd be equivalent to us just basically dividing the top and the bottom by 5. So we get 3 minus 7I all over 5. And this is the simplified form of what we started with, okay? Notice there's no more imaginary numbers in the denominator. All right, we're going to do a couple more of those because I know this can be kind of confusing. So in example number two, the denominator is now a binomial. So we have to use the complex conjugate of 1 minus 2i. What is the complex conjugate of 1 minus 2i? 1 plus 2i. So I just switched the sign. That means I'm going to multiply both the numerator and the denominator by 1 plus 2i. 1 plus 2i over 1 plus 2i. There's our equivalent of 1 fraction. This time we have to do some FOIL. So, man, a lot of mathematical manipulation going on here, okay? So here's what we're going to do. We're going to do a little bit of FOIL, and then we're going to simplify. So in the top, we get 5 plus 10i plus 8i plus 16i squared. Again, I'm going to hold off with that I squared. On the bottom, I'm going to get 1 plus 2i minus 2i minus 4i squared. Now I can combine like terms and simplify, okay? So I'm going to combine these together first, and I'm going to simplify that I squared part. I'm going to do it at the same time, okay? So this is going to become minus 16, and this is going to become 18i. So 5 minus 16 is negative 9. Excuse me, negative 11. Goodness, Mr. Burns. Negative 11 plus 18i. And in the denominator, we're going to get, that's going to go away. We're going to get plus 4. I'm going to 5. 1 plus 4 is 5. So at this point, I would look to see if there's anything that I can divide every term by. Nope. Guess what? There it is. All right. Take a second and just make an observation about what happened there. We're going to do one more. Okay. Again, we're going to multiply by the complex conjugate, which in this case is 4 minus 3i. We're always looking at the denominator. So 4 minus 3i over 4 minus 3i. We've got some more FOIL work to do here. More FOIL. You ready? Let's change the color. Purple. Yeah. All right. So I've got, if you want to put it in parentheses, you can, if you're used to seeing parentheses or if that's important to you. We get 12 minus 9i minus 8i plus 6i squared. That's our numerator. Our denominator is 16 minus 12i plus 12i minus 9i squared. A little bit of simplifying. Remember how it goes? I squareds become negative 1, and we combine the I terms together. So we get 12 minus 6, that's 6 minus 17i. That's my numerator. In my denominator, 16 plus 9, that would be 25. Can I simplify? Nope. 17 is prime. So guess what I just found? I found the simplified form of 3 minus 2i divided by 4 plus 3i. All right, you'll get some practice with this, hopefully on your independent practice sheet. If you have any questions, you make sure you contact me, okay? But there is one last thing I want to talk about. What happens when I is raised to a power greater than 1? What do? You could still simplify that, okay? But it always does come back to making it into I squared, because we know I squared is equal to negative 1. One of the things I want you to remember is that two things, actually. We have the power to power property, right? Power to power. Power to power says that if I have x to the m raised to the n, that's x to the m times n, right? So that's going to come into play here. The other thing I want you to remember is if you're raising negative 1 to an even power, it's going to be equal to positive 1. And if you raise negative 1 to an odd power, it's going to be equal to negative 1. So those two things are going to help us figure out what to do, okay? So here's what you're going to do. Let's consider this. I to the 29th, okay? So what we want to do is we want to change I to the 29th into an expression that starts with I squared raised to some kind of power here, okay? So how close can we get to 29? What number can I put in this blank space right here, right? That would get it as close as possible to 29, right? So 2 times 14 would get it to 28, right? Well, what would we need to multiply I to the 28th to get I to the 29th? Well, we'd have to multiply it by another I, right? Or an I to the first. So I started with I squared. I raised that to a power that gets it as close as possible to 29. And then I had to fill in with what was missing, okay? So sometimes an I is missing, like in this case. Once we get down to this point, we know that I squared is negative 1. So negative 1 to the 14th times I is what we really have here. And we already know that negative 1 to an even power is going to be 1. So this would be equivalent to 1 times I. And 1 times I is equal to I. So I to the 29th is equal to I. That's interesting, isn't it? Let's just do like another example here. What if we had I to the 32nd power? I to the 32nd power. Remember, we're going to raise it I squared to something to get it as close to 32 as we possibly can. Okay, so I squared to the 16th is 32, right? I to the 32nd, so we don't need to add another I. So we have negative 1 to the 16th. Negative 1 to the 16th is 1. So I to the 32nd is equal to 1. There are really only 4 possible outcomes that you can get, okay? You can get negative I, 1, I, or negative 1. These are the only 4 possible outcomes of raising I to a certain power. So if you get something else, you know you did something wrong, okay? And there is a pattern to it. Some people like to use the pattern. Negative I, 1, I, negative 1. And then it starts over again. Negative 1, I, negative I, 1, I, negative 1, negative I, 1, I, negative 1. But this algebraic approach is a much faster approach, especially if our exponent is a really, really, really big number, okay? So this is analyzing larger powers of I. Now, this is going to conclude our lesson. I would love for you to go ahead and do the practice page that's in our Schoology folder. Check the answer key. See how you did. If you have any questions, contact me. If not, go ahead and do that exit slip and see how you do. Have a great day, everybody. I'll see you